but let's go ahead and do our last lecture. The end of geometry. So our last class today is on analytic geometry. Now, what is analytic geometry? Remember, we're done with geometry proper. We finished planar geometry. Last time we talked a bit about solid geometry. Now we're completely shifting gears to another field, and it's just meant to give you a taste of analytic geometry. Analytic geometry would be a full course in and of itself. And that would be a very natural choice for tonight if you want to continue with geometry. Analytic geometry would be one that we could very easily pick up with and move forward with. Intuitively, what is analytic geometry? It is now combining numbers with geometry. It's coordinatizing the plane and then representing geometric figures now with equations for the first time. A little bit of history of analytic geometry. The person most credited with its discovery is a man by the name of René Descartes. And that's why it's sometimes called the Cartesian coordinate system. That's coming from René Descartes' name. And so, a little bit of his life, he was not a particularly healthy person. He struggled with disease most of his life, and he found the way that geometry proofs, that you have to do them, he found them very tiresome. When you come across a geometry proof, you often have to sit there, think about it, come up with some clever way of seeing it, and you have to have a special epiphany for that proof. You have the epiphany, you solve the proof, and then you move on to the next geometric problem. And it's not very often that the previous problem helps you figure out how to solve the next problem. And you once again have to have this intuition, this breakthrough, this epiphany to solve the next problem. And he was very tired of doing it this way. And so he came up with a system, which we now call analytic geometry, which enabled him to start using numbers and start using algebra to solve geometric problems and to start constructing geometric proofs. And so today we will just be introducing the very foundations of that. Now, I know that you are already very comfortable. In fact, you're far more comfortable with instantly starting with something like this and putting all your ticks on and going crazy. And you're more comfortable with that already than you are with just standard geometry. I want you to put that out of your head the best that you can. And now we're going to think about very concretely how we would actually achieve this type of coordination, setting up this type of grid in space. So right now this space is just space, no coordinate system on it. And we're going to come up with that process and what we mean by a coordinate.
You need topology to do that?
Now, geometry is a much stronger structure already than just a topology. A geometric space already encodes a lot more than just topology. Just a topology. Okay, so to start with, we're going to start with coordinatizing a line. So kind of one-dimensional.
Okay.
How do we coordinatize a line? So we start out with some line here.
You pick a point on the line and start counting from there.
Well, first thing we need to do, counting what?
You find a measure that you can count from.
So we got to start with a unit. What is a unit?
It's a segment.
It's just some segment. So here is my unit. It's just some segment. There's my unit. Now I come to my line, and I pick a random point on the line. It's completely arbitrary. I pick that point, I'm going to call that point O. Now, I pick a side of O that is the same length as this segment. I find the point that gives me a segment congruent to this on a side of O. So pick one, here it is. And I mark a slot. This is the same big as that. And I call that point P sub 1. With me? Now, the way we coordinatize this line is from here on out for any point P sub x you choose. For any point P sub x you choose, the coordinate we assign to it is the length of the segment P sub x to O. If P sub x is on the same side of O as P1. So we say that this now has coordinate x. P1 is on the same side of P1, and its distance from O is 1 unit. That's how we chose it. So its coordinate would be 1. This point right here would be, if that's a point P sub 2, its coordinate would be 2. This one its distance from O is x. It's this point, piece of x, its distance from O is x, and so it's given coordinate x. And that's how we coordinatize this side of the line. If you pick a point over here, if my piece of x prime, we'll say, if you pick some point on this side of O, it's on the opposite side of O as P1, then the coordinate we assign to it is negative its distance from O. So if this distance was x prime, then the coordinate we assign to it is minus x prime. And so this point over here, if its distance from O is 1, we assign it the coordinate minus 1. Now, as a matter of convention, when we do this, we write our line horizontally, and we choose the right-hand side to be what we call, we pick our piece of 1 on the right-hand side. We pick our piece of 1 over here. So then we can mark off all the points, and we call that the positive half of the line, and we call that the negative half of the line. And so there, here would be your point, here would be coordinate 1. Do not get confused between a coordinate and a point. They're two very different things. So I take this point over here, call that the point A. A is this point. What is its coordinate? Its coordinate is the number 1, 2, 3, 4. 4 is its coordinate. The point is A. A point is a geometric object. A coordinate is not a geometric object. It is a number. That is coordinatizing a line. Good?
Yep.
Okay. Next, let's move on to, sorry, let me just halfway keep track of this so that we're doing it the same way as the book and I don't accidentally skip anything. So let's see, we just talked about coordinatizing a line. Definition, okay, so yes. Next we're ready to talk about coordinatizing a plane. So now how do I coordinatize a plane?
Take two perpendicular lines.
You start out with two lines perpendicular to each other. Any two lines perpendicular to each other. There's two lines perpendicular to each other. I call O on both these lines where they intersect. There's O. Now I coordinatize both of these lines the exact same way we coordinatize this line. Oh, we skipped a very important step.
You have to make sure your negatives are on the same side.
Picking your segment length.
Picking your unit. So
Yeah.
always got to pick a unit. There's my unit. Okay, now I can coordinatize both these lines using that segment. So I can come and start coordinatizing, say that has coordinate 1, 2, 3, 4, 5, and we can coordinatize both these lines exactly how we did over here. And once again, this could be the point right here that has coordinate 1. This could be the point that has coordinate 2. This could be the point that has coordinate 3. This could be the point that has coordinate -1, -2, -3. Similarly, on this line, this could be the point that has coordinate 1, 2, 3, 4, and these could have been the ones that have -1, -2, -3, -4. And here's a way to coordinatize a plane. Well, here's how we start.
Well, now you have to figure
Well, before we talk about the actual locations of points, as a matter of convention, we choose, when we coordinatize a plane, to draw our lines oriented this way. And we choose to coordinatize it in such a way that all the positive coordinates on this line are on that side of O, and all the positive coordinates on this line are on that side of O, where O is our origin.
do we label O as having the coordinates 0, 0?
We'll get to assigning two coordinates to a point. We have not talked about assigning two coordinates to a point yet.
But
Right now, the only things that have coordinates are points on these two lines.
so does O have a coordinate?
Yes, O has a coordinate on this line, namely 0, and O has a coordinate on this point, or on this line, namely 0.
Guess how far away is it from itself?
So that is currently, we do not have the notion of what are the coordinates at this point. We haven't talked about that yet.
Yeah.
And that I think is the next thing we'll talk about after we name some of these things. We name one of our axes the axis of abscissas. That's first, sorry. We call this the axis of abscissas, and we call this the axis of ordinates. So each coordinate on here is an abscissa, and each coordinate on here is called an ordinate.
Where do those names come from?
What is the etymology on those names? The way that these words evolve isn't particularly natural. Abscissa somehow means to cut, or to cut a line, and ordinate somehow means the line that cuts.
I guess that kind of makes sense.
It's the etymology on it, it's not particularly clear how exactly these words evolved.
So is that
I've also seen some speculation about how they somehow means, this one somehow means first and this one somehow means second. That one would make more sense, but I'm not completely clear on the history of where these words came from. I'm trying to briefly look into it, and there's different ideas. But this terminology is older terminology. You only see it in older textbooks, or you see it in more advanced textbooks. Chances are you haven't seen that terminology before. As a matter of convention, we typically label the points on this axis. When we symbolize them, we typically use an X. That convention has caught on so hard that you are now comfortable with me calling this the X-axis. It's the axis where we typically symbolize what's on it with an X. And similarly, you're comfortable with calling this the Y-axis. And that, for whatever accident of history, just caught on in a major way, and now everyone's very comfortable with that type of labeling. So what can we do for you?
Do you guys have a yardstick in here?
We do not.
Okay. Handing you.
We also use A and B for points too, don't we?
Yes. So René Descartes, he's also the one that introduced using A, B, C, and D, letters at the start of the alphabet, to represent numbers that are known quantities or constants, and using letters at the end of the alphabet like X, Y, and Z for unknown quantities for variables. And you're also very used to just that convention. A lot of conventions that you're just comfortable with because it's what you grew up with. But completely arbitrary. There's nothing special about X, there's nothing special about Y. I could have just as easily called this the U-axis and this the V-axis. Or some of you who have done some physics are probably comfortable with calling, well, usually do time this way, this is the T-axis. But whatever. Nothing holy about those names, nothing special about those names, just the way that they're commonly referred to. Okay. So now that we've got that, let's talk about how we actually assign a coordinate now to some random point out here. So let's think about this very constructively.
You're going to create two.
How would I say where this point is? What does a coordinate intuitively give you?
Location.
It gives you the location of a point
And the distance.
relative to another point. See, it's so weird that analytic geometry is so useful. There's nothing obvious about this being a useful thing to do. Because when we talk about this space right here, it does not make sense for me to talk about the absolute location of this point in the universe. Where is that point in the universe? How do you tell someone where that is? Now we could choose to coordinatize some space, and I could set up my coordinate system, and I could say, well, this is at the coordinates 5 meters this way, 3 meters that way. And you say, okay, there's where it is. But you're not really any further, because that just tells you where it is relative to this point. And where's this point at? And how do you tell someone where that point is? And it kind of just pushes the question back one more. Space, in this sense, this is what we mean by space is relative. Imagine I gave you some sci-fi walkie-talkie that can instantly communicate anywhere in the universe with some other walkie-talkie. You have one end, and I give it the other end to some alien somewhere in the universe. Your job is to meet this alien. So you're talking to the alien on the walkie-talkie, and you're trying to tell him where you are. and you could tell him your position relative to the Earth. Go ahead. We're missing Caitlin. Thank you. Thank you. So you could tell him, given your longitude, latitude, and altitude. You say, this is where I am, alien. And they say, perfect. That's where you are relative to the center of the planet. Where is this planet Earth you're talking about? Okay, it's easy. It's the third rock from the sun. The sun? What's that? Oh, well, in the Milky Way galaxy, if you go into this arm and give it the exact location, okay, that's where the sun is relative to the center of the Milky Way galaxy. Where's that? Well, when you look at this galaxy cluster, it's this one. Okay, that galaxy cluster, where's that? And unless you and this alien can somehow agree on some starting point, there's no way for you to tell the alien where you're at. That's what we mean by space is relative.
Is there no center of the universe?
There is no center of the universe. This gets into the topology of the universe as we currently understand it. As we currently understand it, the universe has slight positive curvature, which means that talking about the center of the universe, this is going to seem weird because we got to switch dimensions. Talking about the center of the universe is kind of like talking about the center of the surface of a sphere. The universe, the best model we have for the universe, to not go too far with you, is the surface of a sphere. Not the inside of a sphere, just the surface. If you could plot out the entire universe, you would use something like the surface of a sphere to do it. Now, it's a three-dimensional surface of a four-dimensional sphere is a better way to do it, but that's too hard for us to picture. So we're just going to use a two-dimensional surface of a three-dimensional sphere. That's easier for us to picture. Where is the center of the surface of the Earth?
It doesn't have one.
Is this the center? Tell me when I got there. And it's kind of a bad question. And so enlightenment, saying what's the center of the universe is kind of a bad question.
Well, if it started with the Big Bang, it had to have started at a single point.
So you can talk about it that way. You can talk about the center of the universe in space and time, in a sense. And you can use the Big Bang as the origin of that.
So the center of the universe is...
So in a way, ignoring, if we stick to just Newtonian mechanics, then we can say time's not relative. Again, just using Newtonian mechanics. And we can say that here's our starting point that we all agree to measure time from. Now, unfortunately, when you include Einstein into the equation, both space and time, it turns out, both distances in space and intervals of time are relative, which is beyond the purposes of this class. That would be completely unintuitive. You should think I'm lying to you right now, and that is the appropriate response to that statement. Length contractions and time contractions are
Weird.
Unintuitive. However, so how you impose a coordinate system on this space, it's completely arbitrary. If you ever go and you take a physics class, anytime you get a physics problem, first thing you're going to do is set up what they're going to call your reference frame, which is you're going to choose how you're going to coordinatize space. And you can do it however you want. There isn't the right way to do it. And yet, it turns out it is an extremely useful thing to do. So just because it's relative does not mean it's not useful. And even though it's relative, it doesn't mean that the results are always relative. For example, I might set up my coordinate system like this. You might set up your coordinate system like this. You with me? Now there's my coordinate system, here's your coordinate system. You and I would completely disagree about where that point is, right?
Yeah.
I would say it's, has coordinates 7-ish. You would say, no, it's clear over here at 13 minus 2. If you're using this and I'm using this. However, if you and I were both looking at this segment here, and if I were to say that segment is 2 units, you would also say, yep, that segment is 2 units, if we use the same unit. And so distance in that sense is what we call an invariant. It's no way dependent upon your reference frame.
If you use the same,
If you're using the same units, but we could both see the meter stick, and we could both agree this is 2 of whatever that meter stick is.
Can you still prove results without the same unit?
Yes, because as long as you can say, I can say, here's my unit, and maybe this was your unit. And you can say, this is 2 of my units. And I can say, yep, that's 2 of your units. And I'll agree with that. And I'll say, and it's 1.5 of my units. And you can agree with that.
Yeah.
So distance is what we call an invariant. It's in no way dependent upon your reference frame. It is not, in a Newtonian sense, relative. So the coordinate system, completely relative. There isn't the right location of that segment. However, there is the right length of that segment. That's not open, that's not arbitrary. And so these coordinate systems, which are completely relative, can enable us to easily talk about something like length, which is in no way relative. And that's the amazing thing that it enables us to do. We can talk about these geometric figures, which in your reference frame and my reference frame, we completely agree on those things. When you and I, regardless of how we coordinate, talk about this triangle, we're talking about the same triangle.
Yeah.
And me using my coordinates and you using your coordinates, we can come to the exact same conclusions about that triangle and about this other triangle. And whether or not they're similar, whether or not they're congruent, if they have the same area or not. So it turns out, even though coordinatizing is completely relative, you can find results that are not relative, that are absolute results. Absolute meaning not relative. Make sense? And that's the kind of shocking part of it. Now you can do this completely arbitrary thing, and yet come to completely non-arbitrary results. And we'll see how that happens. But, sorry, kind of went off on a tangent. We're back to, what are the coordinates of this point in my space?
They're the distance from O on the y.
Let's, tell me exactly how we would do this. I'm out in a field, we've agreed on our unit, and we're trying to find what are the coordinates of that point. How exactly could we do this?
Create a line perpendicular from X. Going to the point.
To say it similarly, create a line through this point parallel to the y-axis,
Or perpendicular.
or to the ordinates.
Oh, yeah.
Parallel to this. Now, since this line is parallel to this line, and I know that this line is perpendicular to this line has to be perpendicular to this line.
Yeah.
So when I do that, this will create a right angle right here.
Yep.
You with me? Okay. We define, remember that this line already has coordinates. So wherever this line intersects here, whatever the coordinate of that point was, we call the first coordinate the abscissa, or the x-coordinate of this point. And so if the coordinate of this point, remember that your coordinate on just this line is just a number a. So we would say that this has the abscissa a, or the x-coordinate a. Similarly, sorry, should have drawn that more intelligently, put it up there. We draw a line parallel to the x-axis, or the axis of abscissas, and where it intersects over here, whatever the coordinate of that point was on this line, call it b, we call this one's ordinate, or its y-coordinate. And that is how we actually coordinatize space. Now I know that you're already comfortable with coordinatizing space, but see geometrically how you actually get that thing, and what it actually means. What does it mean to say that this point has coordinates a, b? It means that if you draw a line parallel to the y-axis, it will intersect this line at the point a. And if you draw a line through that point parallel to the x-axis, it will intersect the y-axis at some point b. That's exactly what it means. That's its definition of it having those coordinates. That makes sense?
How do we know for sure that there are coordinates between the whole numbers?
We already got that with the completeness axiom. The completeness axiom, going all the way back, was pick any real number, essentially, pick any real number you want, there's a segment with that length.
Okay.
So, pick any segment of length I want, A. Pick any segment of length I want, B. I'm guaranteed that then there's that coordinate, AB. Make sense?
Yeah.
Okay, so now we are going to start talking about the equations of lines. Notice, let's look at this line right here. Focus on this one. What do we know about that line?
The line segment from the point to the x-axis has the length of OB.
So if I pick any point on this line, notice that all those points lie on that line. Sounds kind of stupid to say it that way. But this is the one and only line that is parallel to the y-axis that goes through the point A.
Yeah.
So every point on this line would have its abscissa, or its x-coordinate, A. Notice the y-coordinates are all sorts of different numbers. If we come down to right here, this is the coordinate A, whatever A was, comma, and I was trying to draw it so it was at height 2.
Yeah.
Right? And if I would have picked this one right here, that's like A, comma, 3/2. And if I would pick this one just above 3 here, here's the point A, comma, pi, where pi is the actual number we know, 3.14159, da 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 da. So every point on this line has its x-coordinate A. And any point that has its x-coordinate A lies on that line. So there is a one-to-one correspondence between your x-coordinate being A and lying on this line. And so we say the equation of that line is the equation x equals A. If you are a coordinate in space, so that your x-coordinate was that specific number A, whatever it was, in this case 1, 2, 3, 4 point, A in this case is something like 4.72691 repeating. Okay, there it is. Some number. A is just some number. But if you are a point where your x-coordinate is A, then you have to be on this line. Because having your x-coordinate A means that the line parallel to the y-axis through you intersects at A. That's what it means to have your x-coordinate A. Am I overstating it? There's two important pieces to this. If you were a point on this line, then your x-coordinate is A. And if I pick a random point in the universe whose x-coordinate is A, I happen to pick a point on the line. There's a one-to-one correspondence between this line and that equation. And so that's what we mean by this is the equation of that line. Understand, an equation is a completely algebraic concept. A line is a completely geometric concept. And we just found out that there's this one-to-one correspondence between at least lines like this and these equations.
Have we talked about equations at all in geometry?
No. I mean only in the sense that we've been using algebraic properties already to talk about distances. But talking about a geometric figure as though it is an equation is a bunch of nonsense. You're comfortable, to jump the gun a little bit, you're comfortable with something like, let's look at the line y equals 2x plus 7. What do you mean look at the line y equals 2x plus 7? That's not a line. That's an equation. Lines are geometric figures. And equations are equations. And they're very different things. And so you get this thinking all muddled up in your head early on, and now I've got to force you to separate those two things. We're going to bring them back together, but separate them to understand them.
Yeah.
So that's why I'm overstressing if it feels like I'm overstressing. Now, similarly, we've kind of made a mess of this picture. We'll just come over and sketch out a new picture. So here's our O. Let's instead look at a line parallel to the x-axis. Doesn't matter where it is, up here, down here. So let's look at a line now, L, parallel to, I'll put arrows on my axes so that we can quickly tell the difference between axes and just lines I draw. Okay, so here's L. I intended it to be drawn parallel to this. Now what do I know about L? It has to intersect this axis somewhere because it's parallel to this line.
Yeah.
Right? And so, wherever it intersects it, based off of how we coordinatize, it has to intersect it at some number. This time I'm going to call it B. What exactly is B?
That's the point where L intersects the axis.
So B is a number, it's not a point. I'm going to be a little bit pedantic for a second.
Gotcha.
Try and get these very clear in your head. What exactly is B?
B is the coordinate where they intersect.
B is a coordinate of this point right here, which we haven't named. Maybe let's name it. We'll call that the point P. B is the coordinate of P on this line. So we started out by coordinatizing a line. P on this line has a coordinate, namely B. And so B is the coordinate of that point on this line, not its coordinate in two-dimensional space.
Yeah.
Okay. And now, thinking about this line, if I pick any other point on this line, what do I know about its ordinate, or its y-coordinate?
It's B.
It's B. And so this one right here might be roughly, I don't know, 1, 2, 3, 4, 5, 6, maybe something 6, comma, B, something like that, would be the coordinates of that point. If we drew our one down here, probably intersected this using our units there at somewhere close to a point with coordinate 6, right? And all these have different x coordinates, but they all have the same y coordinate. And so we represent that line now with the equation y equals b. Y equals b is a line parallel to the x-axis whose coordinate, where it intersects the y-axis, is b. And once again, for the same reason that x equals a uniquely identified this line, y equals b uniquely identifies this line. If I pick any coordinate in two-dimensional space that has its y-coordinate as b, it's going to be on this line.
Yep.
And similarly, if it's on that line, it has its y-coordinate b. So if it satisfies this, it's on that line, and if it's on that line, it satisfies this. A one-to-one correspondence between these two things. You with me? Okay. So we've talked about the equations of lines parallel to the y-axis, and we've talked about equations of lines parallel to the x-axis. The next thing to talk about is just equations of lines in general. Before we do that, let me ask some trick questions now. So trick question time. So I coordinatize space.
Okay.
Question, what is the coordinate now in space of this point? What is the coordinate, the two-dimensional coordinate of that point?
Isn't it just
If its coordinate on this axis was a.
it's a comma 0?
A comma 0. What does it mean to say it's a comma 0?
That means that's on the line A.
It means that, what does it mean for its coordinate here to be a? That means draw a parallel line to this axis, and it goes through the point here, whose coordinate on this line was a. Similarly, what does it mean for that to be 0? It means draw a line through that point parallel to this axis,
And it goes through.
and it intersects on here, the point O, which on this line had coordinate 0. And so you can also see with this definition why now we can say our origin has coordinates 0, 0. That comes from the way we coordinatize these lines. It's not something that we need to define to be the case. It's something that turns out to be the case because of how we coordinatize. Okay, so now, we've done some special cases. Now the next thing we need to do is to show a one-to-one correspondence between what we now call linear equations and lines in our geometry. So take any equation now of the form ax plus by plus c equals 0. We call these linear equations. Now it turns out that there is a one-to-one correspondence between any equation like this you choose and a line in geometry, and the coordinates on a line that satisfy that relationship, I should probably say.
Do we need to talk about
Where a is not equal to 0 or b is not equal to 0. So they can't both be 0. At least one of them is not 0.
do we need to talk about functions before we can talk about these kind of equations?
No, we'll leave it at this. Okay, so before we jump into that, let's just play with one. Give me an a.
4.
Give me any number you want, so 4. Give me a b.
7.
7. Give me a c.
3.
So you just gave me 3 numbers, a, b, and c, where at least one of a or b was not 0. My claim is you just gave me that there is some line that exists in space such that the coordinates on that line perfectly satisfy this equation. They satisfy this equation and only this equation. No other equation unless it was a logically equivalent equation, somehow the same equation. So let's quickly get comfortable with that. For the sake of, I'm going to pick numbers that just make it easier for us to do the arithmetic in our head. Okay?
Okay.
So I'm going to pretend that you guys said 8 for this, obviously. And we'll also make this like a 4. Okay. Just to clean it up a little bit, make it easier for us to quickly work with an example. Okay. quickly divide everything by 4. I'm going to solve for y really quick here to get it in the form you know and love. You with me?
Yeah.
So maybe I'll really quick subtract the 4x to the other side and subtract the 4 to the other side. So we'll start with that. So this is 8y equals minus 4x minus 4. Divide everything by 8. And I get y is equal to minus 1/2 x minus 1/2. You with me?
Yep.
Okay, so now let's think about all the coordinates in space that satisfy this equation. So I'm going to test. Over here we've got the point minus 10, minus 10. If I plug in negative 10 for x, do I get negative 10 for y?
No.
No. So negative 10 is not one of the points that satisfy this expression. I need to find all the points that satisfy this expression. You with me?
Yeah.
So let's find some that actually satisfy it. So if I plug in 0 for x, notice y is then going to be minus 1/2.
Yep.
So 0 minus 1/2, that seems to be a point on the line. We'll roughly use this as our unit. Or not a point on the line, I need to be careful how I say this. That is a point
In space.
whose coordinates satisfy that relationship. The equation is just stating some sort of relationship between the two numbers.
It's a relation.
Right? And what about if x here were 2? What's 2 times minus 1/2?
Oh, it's
Negative 1 minus 1/2 is
Negative 3/2.
minus 3/2. So when we plugged in a negative 2 for x, then it was minus 3/2 somewhere down here like that, right?
yeah.
Okay, let's go ahead and plug in negative 1 for x.
Equals 0.
Negative 1 times minus 1/2 is positive 1/2. Minus 1/2 is 0. So when we plugged in, what did I plug in negative 1? So that point satisfies this relationship. And if I sat here and carefully did it for all the points I could think of, it would turn out that these were those points that were showing up. And if I picked any point, and it turns out it gives us, if we plotted all those points, all infinitely many, we would be plotting that exact line.
How do we prove that?
Right, so maybe we happen to pick some equation that happened to give us a line. That doesn't mean that if you would pick different numbers, A, B, and C, maybe the ones you guys initially gave me, it wouldn't have worked with. Maybe this is just a weird coincidence of this one equation. So how do we show that for any equation you give me, A, B, and C, it gives me a line? You understand the question?
Yeah.
That's what we're now going to prove. So, we'll start out with, let ax plus by plus c equals 0, where a is not equal to 0 or b is not equal to 0. At least one of them. With me so far? Now we've got to handle 3 cases. I've got to handle the case where a is 0, I've got to handle the case where b is 0, and I've got to handle the case where neither of them is 0. Good? Okay, so case 1. If a is equal to 0, what does that give me? Let's look at this equation where you happen to give me the number a, or you happen to give me 0 for a. So maybe you gave me 0, 14, 19. Maybe those were the numbers you gave me. You with me?
Then b isn't a 0.
So it would be by plus c equals 0. Right, so if a is 0, b for sure is not 0.
It gives you that y is equal to.
So
negative
then,
over b.
just write this equation, yeah. So now we're just going to solve this for y. Subtract c from both sides, and I get by is equal to minus c. And now, since b is not 0, I can divide both sides by b, and get y is equal to negative c over b.
Yep.
So if a equals 0, then y is equal to minus b over c.
Other way.
Thank you. Minus c over b. Right?
Yep.
What do we know about this equation?
It's just the line.
That is a line parallel to the x-axis. We already talked about the special case where x equals something and where y equals something. We've already handled those as special cases. I've already shown you how anytime you have x equals a, that signifies one and only one line parallel to the y-axis. Anytime you have y equals some other number, this is just a number, it doesn't matter which number it is. Anytime I have y equals just some number, that gives you one and only one line parallel to the x-axis. So in this case, we're done. So this gives me a line. And we know what line it is. It's the line that goes through minus BC, whatever that is. Is minus BC, is this a positive or a negative number?
That's,
We have no idea. It depends on what the B's and the C's you chose are.
yeah.
If you chose B to be 10 and C to be minus 5, then minus 5 over 10 is negative 1/2. Make it negative is positive.
Yeah.
So this is neither a positive nor a negative number. It depends on the B's and the C's there. So don't read too much into that sign. So this could be the line y equals negative B over C.
Negative C over B.
B's come first, right? So I keep messing it up. C over B. Thank you. Keep correcting me. Okay, so we've handled that case. Case 2. Case 2 is going to be where B equals 0. If B equals 0, what do we have?
X is equal to C over A, or negative C over A.
Right, x is going to equal negative C over A. Let's just make sure we see that. If B is 0, plug 0 into there, then it must be something in the form AX plus C equals 0. Subtract C from both sides, we get AX is equal to minus C. Divide both sides by A, which, since A is not 0, we can do that. Because if B is 0, A is for sure not 0. And that gives us that X is equal to minus C over A. Once again, we already know what that looks like. That looks like a line parallel to the y-axis, with the coordinate where it intersects down here is negative C over A. Right?
Yep.
So we already know that that gives me X is equal to some number, which we've already talked about, gives us one and only one line. So now, we need to handle the case where you give me numbers where A is not 0 and B is not 0. So for case 3, I have A is not equal to 0 and B is not equal to 0. And now I need to show that this gives us one and only one line. You with me?
Yep.
Okay, so first off, make it very clear what we're saying here. I'm saying all the x's and y's, when A is not 0 and B is not 0, all the x's and y's, all the coordinates whose x's and y's satisfy this equation, lie on one and only one line. You with me?
Yeah.
Now, looking at this equation, there's 2 points I instantly know satisfy that equation. When x is equal to 0, y has to be equal to
Negative C over B.
negative C over b. And when y is equal to 0, x has to be equal to
Negative C over A.
negative C over a. So, I know that the point down here, when x was 0, or sorry, this is y 0. So I know the point, get rid of that so we don't think it's part of it, minus C over A, comma 0. Here's one point that satisfies this equation for sure. And I'm drawing these in somewhat arbitrary locations. I don't really know where that point is.
Yeah.
And for the other one, I'll draw it up here, because why not? This is at 0, comma, minus C over B. So I know that these 2 points for sure satisfy that expression. You with me? Now 2 points uniquely define a
Line.
line. So here is the one and only one line that contains
Those 2 points.
those 2 points. What I need to now show is that any other point you pick on this line, x comma y here, must also satisfy that equation. That's what remains to be shown. If I can show for any other point x, y, whether you pick it here, 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 wherever you pick it, if I can show for any other point x, y you choose on this line that it satisfies that equation, then we found a line that satisfies the equation. You with me?
Yeah.
So now, pick some point on there, x comma y, let's prove that it satisfies that equation. That's what we need to do, prove it satisfies it. Okay, so let's think about how we're going to do that. First off, going to make 2 right triangles here. How do I want to do this? sugar. Oh, we didn't talk about the quadrants. Should have followed in the book a little better. Oh, because I'm thinking about it backwards. No wonder I'm confused. Sorry, thinking backwards. I chose xy so that they satisfy this equation. I need to prove that xy is on the line. That's what I need to do. I'm finding the line that satisfies that equation. We're going to go the other way here in a second. That's why I'm confusing myself. Okay, so I don't know. Maybe xy is right here. Maybe xy is right here. I need to prove xy is in fact on this line that goes through these 2 points. Okay, the way that I'm going to do that is I'm going to construct a right triangle to xy starting at this point, and I'm going to construct a right triangle to this point starting at this point. So both these right triangles, whether it looks like this or like this, they both start from this point. I'm always starting my right triangles from this point. Now here's the correct picture, but a false picture would be creating a right triangle like this, showing that this is not the right one. Okay, how would I know that the triangle using this point is on the same line as the triangle using this point?
You can try and prove that the triangles are similar.
Prove that the triangles are similar. That's exactly what we're going to do. If I can show that the angle from here to this point is the same as the angle from here to this point, then they must lie on the same ray. And if they lie on the same ray, they obviously lie on the same line because the rays have a line. So I need to show that the angle from here to here to here is the same as the angle from here to here to here. If I can show that, then this point must be on this line. And I will have showed that if I can show that this triangle is similar to this triangle. If I can show those 2 triangles are similar, then obviously that angle is the same for both triangles. So I'm going to be showing similarity. Now I know that this is a right triangle, and I already know that this is a right triangle. How much information do you need to show that 2 triangles are similar?
Just their 2 angles.
You need to show 2 angles are congruent, or 1 angle and
2 sides.
2 sides are proportional. So what I'm going to do is show that the 2 sides are proportional. I'm going to show that this side over this side is equal to this side over this side. Or in other words, the rise over the run of this triangle is equal to the rise over the run of this triangle. Or in other words, the slope of this triangle is the same as the slope of this triangle. Understand, slope arguments ultimately rely on similarity between triangles. That's the ultimate connection I'm trying to walk you through there. The slope, showing the slopes are the same, is showing 2 sides are proportional. That's what it is. Okay, so let's do that now and prove that that is in fact the case. So let's look at the slope of this triangle. What is its rise here? What's this distance?
It's negative C over B.
Negative C over B. And what's its run? What's this distance?
Negative C over A.
If
Negative
C over
just C over A. It's the negative of whatever that is. Understand, we should really be using an absolute value around these things. So technically, if I drew my picture different, we could have drawn my picture with a positive slope and my picture with a negative slope. So technically, I should handle 2 cases. I'm just going to handle this case. But there are technically 2 cases to handle. I just don't want to work with absolute values because I'm afraid it'll confuse more than it helps. So the distance from here to here is C over A because that coordinate is a negative coordinate. It's just like if I did this on the x-axis, and you know that this went through the point up here 1, and this was a coordinate minus 2. What's the distance from here to here? 2, not minus 2. So it's the number without the minus sign. It's the number without the minus sign. Okay, now, so that's rise over run of this thing. I need to prove that that is equal to rise over run of this thing. But let's just see what this equals really quick. So what is that equal to? When you divide terms, taking a fraction and dividing it by a fraction is the same thing as multiplying by the reciprocal. So this is negative C over B times,
A over C. So that's the same as negative A over B.
so the C's go out and it's negative A over B. Good? Okay, now let's do that for our larger triangle. So for our larger triangle, what's its rise?
Y.
And what's its run?
X.
This is x
X plus C
negative
over
C,
A.
right?
plus c over a.
C, right?
Remember, c over a is this distance, x is this distance. X plus c over a is that distance.
You could have chosen negative C over A to be on the positive side of X, couldn't you?
You can, but then you have to be careful in how you reason about the slope being negative. So you're going to have to deal with it one way or another. There's no way to do it all in one picture. You have to break it into two cases because it's absolute values and you have to handle the positive and negative case. There's just no way around it if you handle all cases. But good enough for what we're doing. Okay, so rise over run, you see, is this, right? I'm trying to prove that this is in fact equal to negative a over b. If I can show that, we're done.
Okay.
Then they have the same slope, so the two triangles are similar, so that angle is the same, so that point lies on that line.
You don't have a B though.
Huh?
Where's your B in that equation?
What? So we still have work to do, but I just want you to understand, if we can show the equation's this, then we finished.
Yeah.
Okay, so showing that it's equal to that is what we finished. Now we have to use our information about our equation, obviously, so what is y equal to using this equation? I'm going to solve for y in this equation. So I'm going to move the ax and the c to the other side. So I'm going to write by is equal to minus ax minus c. With me so far? Then just divide by b, and I get y is equal to negative ax minus c over b. I'm going to write that one more way that's just useful for our specific purposes. I'm going to factor a negative out of the top. So this is negative ax plus c over b. Just factored the negative out of the top. You see all that?
Mm-hmm.
So y is equal to this. Now substitute that in for y up here.
Okay.
Okay, so this is equal to ax plus c over b, capital B, make it negative, all over,
X plus C.
I make it a common denominator down here.
Okay.
So rather than writing this as x plus c over a, I'm going to multiply x here top and bottom by a. So it's going to be over ax plus c all over a for my denominator. I just multiply this x top and bottom by a.
Oh my word.
What's happening?
They cancel
It's
out.
coming out. All right, so now this is equal to, we got negative, our top fraction, ax plus c over b, times the reciprocal of our bottom fraction, a over ax plus c. And now we see this term, this factor and this factor cancel each other out, and we're left with negative a over b. Da, 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 da. There it is. It came out the same. So the slope to this point is the same as the slope to this point, so the triangles are similar, so this point in fact lies on that line. So I found 2 points that were for sure satisfied that equation. Use those 2 points to get a line, and I showed that anything else that satisfies this equation also lies on that line.
But that doesn't prove that everything on the line.
We've gone one direction so far. Yeah, I got confused trying to do both directions in one go. So far we showed everything that satisfies this equation for sure lies on the line.
Mm-hmm.
But maybe there's also points not on the line that also, or sorry, maybe there's points on the line that don't satisfy that equation. We showed that everything that satisfies that equation lies on this line. Fine. That doesn't necessarily mean that if I pick a point on this line, it satisfies that equation. That's the direction we still need to go. Okay, so this is one proof. Now we're going to go the other way with the other proof. I'm going to prove that for any line you choose, there is one and only one equation of this form that all the points on line satisfy. So, we've shown you got the equation, that gives you a line, or at least points on line. I need to go the other way now. Get the line, you should be able to get an equation from that line. That's the direction we're going. Okay. And this is where we're going to derive the formulas that you are going to want to write down and that you are going to need to use on your test. It's a very useful thing to do to come up with the equation of a line. So, go in the other direction now. We're starting out with a line. I need to pick a random line, any line. Here is some random line. I need to prove that that line has an associated equation. Okay? Now, since it's a line, what do I know about it?
It has 2 points.
It has 2 points on it. So you choose the line. I close my eyes, you come up here and you drew a line. I don't know why I can't watch you draw. Okay, there's the line you gave me.
Yeah.
Now I say there's for sure 2 points on that line. So you have to give me 2 points. And you say, okay, fair enough. I'm telling you for sure there's a point on the line. I'm telling you for sure there's a point on the line. So you for sure gave me 2 points, right?
Yep.
And since you for sure gave me 2 points, I can for sure draw the line through this point parallel to this, draw the line through there parallel to that, and vice versa for this, and discover the coordinates of those points, right? So let's say that when we went through this process, finding the coordinates of this point turned out to be x1, comma, y sub 1. Those are constants, not variables. Those are the actual coordinates of some point, like -5, -3, whatever it is. Similarly, whatever this other point is on the line that you gave me, it has to have some coordinates called x2 and y2. Okay, that's all I know so far. Using that information, I need to come up with some equation for this line. You with me? So now, we'll continue it on just to follow the convention we did before. Doesn't matter where I choose my x, y, but I'll choose it for now. Doesn't matter. So now I need to show that for any other point on this line, I need to come up with the equation that it satisfies, well, for any point on the line, x comma y now. So x comma y now is going to be any point on this line. I need to show that there's an equation, some relationship it satisfies, that coordinate. I could have chosen that point as my xy. I could have chosen that point or any other point along this line. Xy is completely random. You with me? Now, once again, wherever this xy is, we can create this right triangle. Right? And so now we can look at this right triangle from here to here, this right triangle, and this right triangle. Looking at those 2 right triangles. Now, since both these points are on the line, I know that this triangle is similar to this triangle. Because this angle is for sure the same for both of them, and they're both for sure right angles if I drew my picture again. So this triangle is for sure similar to this triangle. So they both lie on the same line, or since they lie on the same line, those are similar, and so I know that the rise over the run for this has to be equal to the rise over the run for that. What is the rise over the run for this? What is this distance right here?
Y plus y1.
What is the distance between the number 13 and 5?
8.
8. How did you get that?
13 minus 5.
13 minus 5. What is the distance between the number 3 and -2? 5. How did you get that? 3 minus -2.
So it's y minus y1.
So to get the distance between 2 points, you do that one minus the height of this one. This is y, this one's height is y, this one's height is y1. The distance between them is y minus y1. You see that? So what is the height of this triangle?
It is
Y minus y1.
Y minus y1. The ending point minus however high the starting point was. Okay. What is the distance from this distance right here?
x minus
X minus x1.
x1.
What is the height of this triangle?
y2 minus
Y2 minus y1. And what is the run of this triangle?
x2 minus x1.
X2 minus x1. Now, I'm going to multiply both sides by x minus x1, by this factor.
Okay.
Okay, so then I'm going to get y minus y1 is equal to y2 minus y1 all over x2 minus x1 times x minus x1. And now you can probably already see it. Look, it's y, you have some constant, is equal to some constant times x plus some other constant. Put your constants on both sides, and you've got some equation. Where it's just y times a constant, x times a constant, and then some remaining constants. So we found the equation. And you've already seen this equation. This is called the 2-point form of an equation. This is how you get the equation of a line that goes through any 2 points. Give me 2 coordinates. Give me two coordinates.
5 and -3.
5 minus 3. So 5 minus 3, that's right here. Give me another coordinate. Preferably something up here, just so it
-2,
contains
4.
my picture. What?
-2, 4.
-2, 4. So here's 2 points. What is the equation of the line that goes through those 2 points? Here's my x1, y1, x2, y2, or whatever.
So you have 1.
Plug it into here. The equation of that line would be y is equal to, y minus y1. It doesn't matter which point we call our x1, y1 point and which one our x2, y2. Pick one.
4.
This one you gave me first, so we'll just call that the x1, y1. Doesn't matter. So y minus y1, y1 was -3, so y minus -3 is y plus 3, is equal to y2 minus y1, y2,
Other way. Wait. No, you're right.
y2 minus y1 is 7. The distance between 4 and -3, in other words.
Yeah.
7 over x2 minus x1. x2 is -2. X1 is
5.
-2 minus 5 is
7.
-7
-7.
times, yes, this thing has what we call a negative slope.
Oh. You're right.
Times x minus x1. What was x1? 5, the number I'm pointing at.
Yeah.
Okay. We happen to pick good numbers here. I don't know if you did that on purpose. But 7 over 7 comes out nice, right?
Yeah.
So this is y plus 3 is equal to -1 times x minus 5. Or in other words, y is equal to -x
Plus 5.
plus 5, but then subtract the 3.
Plus 2.
Plus 2. And so this is the line, the way that you know it, that goes through 2 here and has a slope of -1. We found the equation of the line that goes through 2 points. So this formula right here is one that if you don't know it like the back of your hand, you're going to want to write down on your notes for the test. Right here. This gives you the equation of a line that goes through any 2 points, where x1, y1, and x2, y2 are the coordinates of your 2 points. We're going to keep messing with this. I just want to point out the equations as we go that you've seen before. Okay. Now, y2, y1, x2, and x1, those are all just constants. Right?
Yeah.
So I've got constant minus constant over constant minus constant, bunch of constants. And when we do the division, we're left with just a constant. So I'm going to take that big mess. I'm going to say, you know a good name for that big mess? M.
Okay.
And so I'm going to rewrite this as y minus y1 is equal to m times x minus x1. Where what is m? It's the rise over the run, or the slope. So here's another equation. This is called the point slope form of an equation. If you give me the equation, if you give me a line, you tell me one point that it goes through and what its slope is, this gives you the equation then of that line.
Yep.
You with me? So this was the 2-point form. This is called the point slope form. 2 points, you get the equation of a line, or a point and slope, and you get the equation of a line. All right. Finally, let's solve for y here. So y minus y1 is equal to, distribute our m through, m times x minus m times x1. Finally, move the y1 to the other side. We get y is equal to m times x minus m times x sub 1 plus y1. Again, you've got the constant times a constant plus a constant. You know a great name for all those constants? No, you were one off. B. It's the perfect name. Can't get any better. And so if we relabel all that stuff B, then this is y is equal to mx plus b. And now what is b here?
It's just your y-intercept.
Notice, when x is 0, if we plug in 0 for x, what does y equal? B. So, it's when x is 0, your y is b. It's the coordinate that crosses on this line, where x is 0. Or in other words, your y-intercept. And so there's the three equations that you know and love and see all the time. So this is the 2-point form, this is the point-slope form, and this is the slope-intercept form. And now, just to get back to where we started, I'm going to rewrite this equation one more way. I'm going to rewrite this, moving all this over to the same side. I'm going to rewrite it as negative m times x plus y minus b equals 0. You with me? That's just moving everything to the same side. You won't need to remember this form of it. But we're just finishing the proof. The proof was pick any line you want, and I can find an equation of the form ax plus by plus c equals 0. I can find an a, a b, and a c such that this line satisfies that equation. And here is that equation. Some number times x plus, you can think about our b here as being 1, some number times y plus c equals 0. So there we go, we found it. For a line that had some slope to it. We already knew how to do it for lines that were parallel to the y-axis and the x-axis. We already handled those as special cases.
Yeah.
So notice what we assumed in this equation is that x1 and x2 were not the same number, and that y1 and y2 were not the same number.
And what happens if you have nonlinear equations?
Well, those can be the same number and still have a linear equation. It's just if x2 and x1 are the same number, then your line is parallel to the y-axis. Similarly, if y1 and y2 are the same number, then your line is parallel to the x-axis. But if you get a nonlinear equation, something like y is equal to x squared, then you're left with something that is not a line. And so that's why we call these things linear equations.
How do we know that's not a line? Like, how do we prove that?
Because we prove that there's a one-to-one correspondence between equations like this and lines. So for every line, there's one and only one equation like this that corresponds with it. And for every equation like this, where at least a or b is not 0, there's one and only one line that corresponds with it. That makes sense? You're going to need to know how to do that for your test. Okay, let's talk a little bit about distance. Hopefully my camera's not dying on me. Let's talk about distance in one dimension. How do I calculate the distance in one dimension?
The difference.
So if we're in one dimension, and I've got a point here and a point here, and the point here has coordinates x1 and the point here has coordinate x2, how do I find the distance between those 2 points?
It's going to be x1 minus x2.
x1 minus x2, let's put a concrete number here.
Okay.
We'll call this -1 and we'll call this 4. How do I find the distance between them? If we did x1 minus x2, then that would have been -1 minus 4 is equal to -5.
Yeah, minus x.
So this was writing x1 minus x2, right?
Yeah.
In this case, if we would have done x2 minus x1, we would have gotten the right answer.
So just take the absolute value that you found.
So we just take the absolute value so that we don't have to keep track of order.
Yeah.
So the absolute value, the way we typically write it is x2 minus x1. Absolute value gives us a distance between 2 points in one dimension. And this works for any 2 numbers you choose. So in this special case, let's pretend that x1 was -1 and x2 was 4. In that case, we would have gotten 4 minus -1 is +1. Take its absolute value and we get 5. Now let's swap. Let's pretend that the x2 was a -1 and the x1 was a 4. Then we got -1 minus 4 is equal to, minus 4. -1 minus 4 is -5. Take its absolute value gives you 5. And so we do the absolute value of the difference gives you the distance. What about in 2 dimensions now? How do I find the distance between 2 points?
That would be the, you have to use the Pythagorean theorem to do it.
Yeah, so let's really quick come up with that equation. So here we are, we've got some coordinatized space, and I've got some point here with coordinates x1, y1, and I've got some coordinate up here with coordinates x2, y2. I'm trying to find the distance between those 2 points. You with me? The distance between those 2 points is the length of this segment. Same thing, right?
Yep.
So how do we do this? We build this right triangle where this line is parallel to the x-axis and this line is parallel to the y-axis, and so this is a right angle. And now, what is, I drew that kind of big, x1 comma y1. What is the distance from here to here?
X2 minus X1.
The length of this triangle is x2 minus x1. What is the height of this triangle?
Y2 minus 1.
y2 minus y1. Is everyone seeing where these numbers are coming from? Okay. And we're going to call this distance right here little d. We're trying to figure out what little d is. But now, from the Pythagorean theorem, I know this side squared plus this side squared equals this side squared. Right?
Yeah.
So d squared is equal to this side squared, which was x2 minus x1, squared, plus this side squared, y2 minus y1, squared. Now, why didn't we put absolute value here for the distances?
We're talking about lines.
You can put the absolute value there, it's perfectly fine. But when you square the absolute value, it goes out, because a squared number is already always positive.
Yeah.
So it was absolute value,
Yeah.
and then we just don't care anymore once we square it. Make sense?
Yep.
Okay, so that's what d squared equals. But we weren't looking for d squared, what were we looking for? D. So d is just equal to
The square root of
the square root of that. And this is called your distance formula.
You're right, square.
Oh, thank you. Let's do a concrete example. So let's say that I've got the point over here. We'll make you have the coordinates, I don't know, -6 and 2, something like that. You with me? Now I'm going to go over to this point here, and we'll make this a point -2, comma 5. Trying to pick numbers that will come out nicely. You with me? So we're trying to find the distance now between these 2 points.
Yep.
Okay, so let's calculate that distance. That distance, whatever we're looking for, call it, we already used d there, we'll call it little c. What's little c here? Little c is equal to the square root of, pick a point to be your x1, y1, pick a point to be your x2, y2. It doesn't matter what order you do it in. So since this one's the furthest left, I'm going to call this my x1, y1. You with me?
Okay.
So it's going to be x2, which is -2, minus x1, or plus 6, squared, plus y2, which is 5, minus y1, squared. What's -2 plus 6? 4. What's 5 minus 3, or 5 minus 2? 3. What's 4 squared?
16.
What's 3 squared?
9.
So c is equal to the square root of 16 plus 9, which is equal to
25.
square root of 25,
5.
5. And so the distance from here to here is 5. Well, I chose numbers that would work out nicely.
How do you extract that formula to the third dimension? Like, you could just add another term, but does that? I'm trying to think of it geometrically how that works.
It's not that hard. The way you do it is you split it in 2. I just don't know if I'll be able to draw this very well. Need something nice and flat. So first off, let's say that the point I'm trying to figure out is from this actual point on the chalkboard to this corner up here.
Okay.
First, I find the distance from here to this point, which I can do looking at this plane.
Yeah.
And now I can find the distance from this point to this point in this plane. And so, now look at the plane that goes through this point, and this point.
Yeah.
And now I can find the distance from here to here in that slanted plane.
Yeah.
It's a bit hard to see. Say that one more time. So I'm trying to get the distance from this point to here. I get the distance from here to here in this point. And now I've got this point, and this point. 3 points to find a unique plane. So take the plane that goes through this point, and this point. That's going to be a plane slanting on an angle, cutting like this. Now in that plane, find the distance between this point and this point using the exact same formula. So you swap twice. And it comes out to be exactly the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And so it just comes out that way.
Could we prove that that formula holds for all dimensions with whatever terms?
Yeah, you can do a proof by induction to show that adding another dimension changes nothing. It just adds one more term. Because you just repeat the process again. If we did it in 4 dimensions, we go in one plane to get the distance to 1, go in the next plane to get our second distance, and then go in the next plane, which now we can't picture, to get your third distance.
Yeah.
Okay, anyways, so the last thing that we need to now talk about is circles and the equation of a circle. So we talked about equations of lines. The only other thing we're going to talk about now is equations of circles. And we need to remember that distance formula to talk about it. So what was our distance formula? The distance between 2 points is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so now let's think about a circle for a second. Let's do a very concrete circle. I'm going to do a circle centered at the origin with a radius here of, well, we'll say 2, just to give some life to it. So let's think about a point here, x1, and what x comma y, what relationship must it satisfy if it's on the circle?
It's the distance of 2 away from the center.
It has to have its distance from the origin equal to 2.
Yeah.
That's what it means to be on this circle. So if I pick a random point on the circle, its distance from the origin is 2. So we can calculate its distance from the origin. So we know that its distance from the origin, 2, is equal to the square root of, let's see, we've got x minus 0. Our x coordinate here is 0. The x coordinate of this point minus the x coordinate of this point. Squared, or in other words, x squared. Plus the y coordinate of this point minus the y coordinate of this point, squared, is equal to 2. Or in other words, we have 4 is equal to x squared plus y squared. That is the way it would actually be written, except for swap the order. The way we write it is x squared plus y squared equals 4. That is an equation of a circle centered at the origin with radius 2. What if its radius would have been 3? What would our equation have been? That would have put a 3 here.
We would have got an S.
That would have put a 9 here.
Yeah.
And that would have put a 9 here. And in general, if our radius had been r, then this distance would have been r, this distance would have been r squared, and this distance would have been r squared. Oops. R squared. So here's the equation of a circle with radius r centered at the origin. Now that was centered at the origin. What if we centered it somewhere else? So let's do this again. And this time we're going to pick a completely random point to center our circle. So let me draw the circle roughly first and say here's our center. Okay. So we draw the circle centered here. We'll pretend that this was coordinate, need to make up a letter h. And the type was obviously k. So it has coordinates hk, which is typically the letters we use to symbolize the center of a circle. Why? Because. Okay, so here's the center of our circle, and it has some radius r. What does it mean for a point, xy, to be on that circle?
It's far away from HK.
Its distance from the point hk is r. That's what it means to be on this circle. This circle is all the points whose distance from hk is exactly r. So I know that r has to be equal to the distance between those 2 points. So the square root of the x coordinate of this point minus the x squared of that point, x minus h squared, plus y minus k squared. Again, square both sides. And this time I may write my r squared on this side. So then we get x minus h squared plus y minus k squared is equal to r squared. That is the equation of a circle with radius r centered at hk. Concrete example. If I gave you x minus 3 squared plus y plus 2 squared equals 25, what is that?
The circle centered at
3, -2.
3, negative.
It's a circle centered at 3 and negative 2. How much did I subtract away from y? I subtracted negative 2 from y. That's how you plus 2.
So it's centered at 3 and negative 2 with radius 5.
So centered at 3 and 2 with radius 5. So extremely roughly sketching it out. So 3, negative 2, we'll say something roughly like that. And then radius 5. Terrible picture. But there it is. Okay? So I don't know what your homework problems are going to be. They're probably going to give you equations like this and say, sketch the circle that satisfies that equation or something like that.
Sweet. Already proofs? How many proofs?
I don't know. Oh, thank you. I missed a proof. One proof that I need to do is the midpoint of a line. This will be the last thing we do. Sorry, jumped ahead. Forgot to talk about the midpoint of a line. Because there are only a couple proofs in this chapter. Proofs about the line and then the proofs about the midpoint and deriving the distance formula. So, once again, let's say I've got some segment and the coordinates of this point are x1, y1, and the coordinates of this point are x2, y2. And we're in some coordinate system. With me? The question is, what are the coordinates of the midpoint here? It's going to be the average.
Yeah, this is 2.
What is the average of x1 and x2?
X.
X2 over 2.
You have the right idea, you just said wrong. x1 plus x2 over 2. Should be its x coordinate, and its y coordinate should be
Y1 plus Y2 over 2.
y1 plus y2 over 2. So that's just using, that's just thinking about, we expect that to be the answer. Now I'm going to prove that that is in fact the answer. You with me?
Yeah.
So I'm going to say, here's our segment, let xy be the coordinates of the midpoint. I need to prove that these are in fact what they are. You with me? Now since it's the midpoint, what do I know about it?
That the distance between either of the two segments are the same.
Yeah, so I know that this distance is the same as this distance. Good. And then look at this triangle that I've drawn. And look at this triangle that I've drawn.
They're similar.
They're going to be similar. And so, well, actually, here's a better way to say it. I know since this point cuts this line exactly in half, if I draw a line through that point parallel to this line, it also has to cut this side exactly in half. You with me? And similarly, since it cuts this line exactly in half, if I draw a line through here parallel to this line, it has to cut this line exactly in half.
So those two.
So I know that this, whatever the x is, has to be half of this. I know whatever the y is, has to be half of this.
Yeah.
You with me? So I know this distance is half this distance. What is this distance? It's just x minus x1. And it has to equal half of this distance. What is this distance?
X2 minus X1.
Similarly, I know that y minus, well, I guess we could say this is half of this. So y minus y1 will follow the same convention, is equal to 1/2 y2 minus y1. Right? And now I'll just solve for x and y in both these equations. So I'm going to start with this one. And let's solve for x. So I'm going to get x is equal to, I'm going to move this to the other side, but let's also distribute the 1/2. it's equal to 1/2 x2 minus 1/2 x1. That's just shooting the 1/2 to both those. And now I move this to the other side, so plus x1. With me? If I have an x1 and I subtract half of x1, what am I left with? Half of x1. I have a whole 1, I subtract half of it, I'm left with half. So this is equal to 1/2 of x2 plus 1/2 x1. Factor the 1/2 out, and this is equal to x2 plus x1 over 2. See it? And then for the y, it's the exact same algebra. So there we go. X is in fact equal to the average of those two, and y is in fact equal to the average of those two. So your intuition was correct. Okay. That's geometry. You finished the whole class. We finished the whole book. You did it.
Awesome.
Maybe just a word of comment about the point of all this. What did we do in geometry?
We studied axiomatic systems.
The point of geometry is exactly that, getting competent functioning in axiomatic systems. We started out talking about logic really quick and set theory, and then we introduced into the class some postulates or axioms. And from there on out, we were saying if the axioms are true, what else is true? And so our earliest proofs, we were using the fact that there's 3 non-collinear points in the plane, and every line has at least 2 points, to prove that there's at least 3 lines in the plane.
Yeah.
And so we took our first 2 postulates, and we proved that those 2 together imply this new statement, which we then call a theorem. The theorems were the statements implied by the postulates. And from there on out, that is all we were doing over and over again. And based from this theorem and this postulate, we were able to get some new theorem. And we created all this web of theorems, all coming from these initial postulates. And so mathematics never says the postulates are true. Mathematics says if the postulates are true, then the theorems are true. That's what's true. Remember in math, we never say all men are mortal, and we never say Socrates is a man, and we never say Socrates is mortal. We say if all men are mortal, and if Socrates is a man, then Socrates is mortal. The whole implication is what we call true. And so in math, we say if these postulates are true, then the Pythagorean theorem. That whole thing is what we mean by true. True with a capital T.
Yep.
We know it to the extent you can know anything. And appreciate what we were able to do in this class. Every single thing I claimed was true, I was able to show you was in fact true. It was demonstrably true. I could demonstrate to you that it was true. You all believe the earth travels around the sun. You have never seen a demonstration of that. In fact, when you go outside and you can watch the sun move around the earth. You don't believe you're lying guys. Right? And so it's very special what we were able to do in this class. Everything I was able to claim was true and tell you was true, you could in fact know for yourself was in fact true. You never had to take my word for it. That was the point of geometry. Plato had inscribed above the entrance to his academy, "Let none ignorant of geometry enter here." Why? He wanted to make sure you knew how to think before you went on to more speculative fields. Because in geometry, if you're right, you're demonstrably right. And if you're wrong, you're demonstrably wrong. It's a very safe playground for you to practice reasoning. Because when you make a mistake, your teacher can catch it and say, "Nope, you were thinking wrong." And it's very easy for me to change your mind in geometry when you make a mistake. When someone makes a mistake in a political position, how hard is it to correct them? They fiercely hold on to those positions and you can't change their mind to save your soul. Hardly. And that's the type of things that you talk about in Plato's Academy, philosophy. One of the things you talk about is politics. He knew it was very dangerous to introduce a youth to politics who didn't at least know how to think first. That's what he was talking about when he said, "Let none ignorant of geometry enter here." You wanted to make sure you knew how to think, not that you mastered memorizing a bunch of geometric theorems. What a waste of time. The point was never to memorize the theorems. The point was to practice thinking and know what it means to know, and to actually know something yourself. And now, when you go on to a more speculative field like politics, you should be very terrified to say that word "no," because you know that you don't know.
Yeah.
Right? That was the point. get you competent thinking, deductively, reasoning, correctly, and introduce you to a safe playground where you can do that. That's geometry. Anyways, hope you enjoyed the semester. It's been fun.
Yeah.
I did.